Hello everybody, I'm going to talk today about ARP protocol or address resolution protocol. If you are familiar with OSI and TCP IP models, ARP is a layer 3 protocol, but in fact it works on the underlay of the layer 3. This gives the ARP protocol the advantage of understanding both layer 3 and layer 2 protocols. Hosts use ARP protocol to request layer 2 address or the MAC address, and each and every host generate and maintain an ARP table on its own. When a host learns the next host's MAC address, it maps them with their corresponding IP addresses and then cache them in its ARP table. This is an example of an ARP table taken from my host PC. It shows the host IP address, its default gateway, and the default broadcast message for the subnet, with corresponding MAC addresses. The all F is the default broadcast message of layer 2 addresses. Let's review the OSI and TCP IP model. That both models are identical in their protocol suites, except that the OSI model has 7 layers, while the TCP IP reduces it to 4, although some tech bodies consider it 5 by leaving the 2 buttons as it is, the link and the physical layer. What concerns us in this is how the data be named technically in each stage of the models. When the host A requests a web page from host C, considering a host C is a web server, the application will be a data. Move the data downwards to the transport layer. On the transport layer, it will be added the TCP and UDP port, depending on the reliability of the data. When the transport layer adds the TCP and UDP, the data will become segment. Then the segment will move down to the next layer, which is the network layer. On the network layer, the IP addresses will be added to the segment, and the segment will become a packet. Packet will never change. It will remain the same, but the thing which is concerning us is when the data link on the data link layer or the network interface layer, the MAC addresses will be added. When the MAC addresses will be added, the packet become a frame. From now on, I will be using these terms and you should memorize them. So the packet must be framed before sending it to the next hop. Why? Because the media works at layer 2 and layer 2 understands only framing language. So any host try to send a data to any other host have to go through these steps. And when the host receives the packet, you go upward from the data link, removing all each layer, removing this and then send it forward upward. The framing occurs when the packet is encapsulated with the appropriate encapsulation header with the source and destination layer 2 addresses. This is an example of an encapsulated packet. The whole packet is encapsulated into a frame. When a host receives a frame, before de-encapsulating it, it checks the destination MAC address. This is a very important thing. If the address, if the MAC address is addressed to its own interface or to a broadcast or a multicast address, then the packet will go ahead and process it, or assuming no errors has been detected within the frame. Anything else other than that is the packet will be dropped. This is the default broadcast addresses. All hosts will send request MAC address for a host to host. The destination address has a broadcast, unless if it is on a multicast subnet. It will send a broadcast, and the receiving host, as soon as it sees a broadcast, it will de-encapsulate the packet and then see what is the IP addresses for the packet. If the packet is the IP destination IP address is its own IP address, then it's processed. If it is not, it will drop it and then ignore the packet. ARP is an run protocol is used within the same subnet to request the next host's MAC address because it is non-writable protocol. When a host, let's say when a host A sends an ARP request to host C using its IP address, it uses a broadcast as the destination address, and only host C will respond based on its IP address. If C is the destination IP address is its own IP address, so it's responded, but all other hosts will ignore the message. In another scenario, if the host A or PC1 on network A try to communicate with PC2 on network D. PC1 knew that the PC2 is on different subnet. So PC1 requests this default gateway MAC address if it's not on the ARP table. Request the router 1's file system net MAC address, and when he gets it, is encapsulate the packet with Ethernet header. This is an Ethernet line, so it encapsulated with Ethernet header and forwarded it to R1's. R1, based on seeing the frame is designed or destined to its interface, will accept and de-encapsulate the frame to see the packets is not addressed to its IP address. So checks its routing table and finds out the packet must be sent through its serial interface. R1 now re-encapsulate the packet with a HDLC header, because this is a HDLC line, and forward it to R2. So packet is encapsulated and forwarded to the receiving device, will de-encapsulate to see where it's heading. ARP by default consists of two messages: ARP request and an ARP reply. ARP request sent by the host is requesting, and the target host will reply by saying, "Oh, my MAC address is here." This is a capture packet shows an ARP request has been broadcasted of all Fs, the broadcast to and broadcast message. If you look further into the Ethernet header, you will see that the host PC is requesting the MAC address of its default gateway. Sender is my host, target is my default gateway, the MAC address targeting the MAC address, so it's sending the broadcast message. So as soon as my default gateway get the message, it will see it's a broadcast message, so it will accept it and de-encapsulate the packet to see what is the packet's destined to. When it sees its own IP address, or it's mine, or what it is asking for, and MAC address, so it's replied with its MAC address. Is saying, "Oh, my MAC address is ARP types." Keep in mind, ARP is a protocol used to get next hop's MAC address using next hop's IP address. There's 4 types of ARP. The first two are inverse and reverse. They are the opposite way of an ARP. So ARP is using layer 3 to request a layer 2, and inverse and reverse are using layer 2 to request a layer 3 or IP addresses. Reverse ARP is the old-fashioned to be assigned an IP address and is replaced by modern DHCP server. The host sent and reverse ARP to get an IP address instead of using a DHCP server. Now DHCP servers take over, so it's an obsolete now. Inverse ARP, on the other hand, is request for host's layer 3 address. Example in frame relay. Hosts use the DLCs to learn next hop's IP addresses. Proxy ARP. Proxy ARP is a node that responds to an ARP request on behalf of another node, pretending to be the other node. When the host sends an ARP request, he would respond it with his own MAC address. Gratuitous ARP is popular in DHCP and used by hosts to detect duplicate addresses. As soon as a host gets assigned an IP address from the DHCP server, it sends a gratuitous ARP to make sure no other host is using the assigned address. It does that by sending an ARP request using the source and destination as the newly assigned address, expecting no other host will send an ARP reply back. If an host sends an ARP reply, that means there is a duplicate the host is using or assigned IP address. Gratuitous ARP is also used with HSRP. And it is disabled by default on Cisco devices. So to enable it, issue the command IP gratuitous-ARP. Now this is a gratuitous ARP broadcasted to the all networks. If we check the IP header packet, we can see that this, the source IP address and the destination IP address are identical. This means that the sender sent his own the IP address has a destination address to check if there is any duplicate on the network.